So the last time we were talking about half-factorial domains. They are atomic. That is to say that every element is not zero, not even factored into irreducible. That's not uniquely. And if alpha I, they are irreducibles, and alpha 1, alpha 2, alpha n, beta 1, beta 2. That's what it makes it here. And example, this is unproven, but I've told this to you. Any UFD is, of course, this, and K and F is always mixed. And in the UFD, it can only K and F. So this is a large class. Now I am going to give you a very famous theorem. This is actually from a paper called A Characterization of Algebraic Number Fields with Class Number 2. There actually probably should be something that kind of jumps out at you. It's a little strange here. How can a number field have class number 2? This is a sloppy kind of terminology the number theorists use a lot. When they say a number field of class number, what they really mean is the ring of integers of that number. This was in a challenge. This question actually came, or this theorem came as an answer to a challenge on Arcadich about asking, okay, what does class number mean? These things arithmetically. Interesting thing about this paper, I actually looked it up, some of the stats. I looked it up on both Google Scholar and on well, I didn't do a very good job on Google Scholar. I looked it up and also on the MathSciNet. MathSciNet's a little bit slow and behind, and also the references don't go back very far. But MathSciNet shows the first reference to this paper in 1993, which is 33 years after its publication. And then the next one it shows is 1999, another 6 years. And then 2000, and then it's the plan. It's all over the place. Google Scholar shows between 200 and 300 citations. But again, the first citation probably didn't show up until about the mid-1970s. And then the citations were all set at zero until later. I'm going to couch this in more modern terms. Carlitz's original result was couched in terms of terminologies developed. What are the ring algebraic integers? So in particular, what he's talking about is the integral closure of Z and a finite series of fractions. R is so that's his problem here. If an only in order to class group less than. And at some time or another in this proof, I am going to use two things that are true of rings of algebraic integers. number one, I'm going to use the order of class group is 5. Number two, I'm going to use the fact that every ideal class contains a prime ideal. I won't even need infinite many. The rings of algebraic integers are much more robust in that regard, since every ideal class has infinite many primes in them. But as a corollary, you can replace ring of algebraic integers with any Dedekind domain where every ideal class contains a prime ideal, and you don't even need the class group to be found. You only need to be torsion. So that is every element has finite order. Proof. And actually, there's going to be an important concept. Actually, I'm going to write up proof a little bit longer in more detail. Carlitz proof is like 2 pages. I mean, not just proof, the paper is 2 pages. If the class number is 1, that means that every invertible ideal is principal, but of course all the ideals are principal, or all the ideals are invertible, they're not 0. And so that one, in fact, this actually shows Carlitz Theorem actually divides rings of algebraic integers up into 2 nice classes. Class number 1, UFD. Class number 2 is HFDs that are not good. Now suppose so that is, I don't know much, but I do know that there is only one group of order 2. And so this is actually more CMOD. Now, let me make an observation. In R, CLR, much more in 2. There are 2 types of irreducibles. And I'm going to go through this because afterwards I'm going to show how you kind of extend this idea. Well, one type of irreducible is might be prime. And there's only one other type. P and Q, non-principal prime ideals. These are the only ways that irreducibles can be formed. They're either as they stand prime itself, or they're the product of 2 non-principal primes. Let me justify the statement. Now, this is part of the magic of Dedekind domains. So I can take principal ideal generated by pi and I can factor into the prime ideals unique. And I'm going to do this way. Well, where capital PI non and little PI yes. Is that fine? I should put that. Now, let me point out that if n I'm going to sort of take n equals 0 to mean that there aren't any of these here, right? If n is not 0, then n equals 1 and pi is 1. Because, for example, you can't have pi equal like 2 primes, can you? Because then it wouldn't be irreducible. Because that would mean pi is a unit times p1, p2, right? Contradicting the irreducibility of pi, right? So if there's even one principal prime ideal involved, there's exactly one. None of these are here, right? Everybody clear on that part? Now, on the other hand, if there's no principal prime involved, then pi well, these are all non-principal primes. Now, can somebody make an observation about what n is? Well, the first thing is, that's too good of an observation. The first thing is n has to be an even number, right? Because all of these are the non-principal class, right? So think of this as in Z2 adding 1 bar to itself n times. This side of the equation is principal ideal, it's in the 0 principal class. That means that n must be even, right? So you can actually pair it. So let me write it this way, n equals a. So has to take on that, right? Now I'm going to go further and say that n must be 1. Let's see what happens. Well, certainly that, and each of these principal, right? So this means pi is alpha 1, alpha k. Therefore, pi is a unit of alpha 1, alpha k. And since pi is irreducible, k must be 1. And this justifies my earlier statement. So when I look at irreducibles in my class number 2 ring of integers, they're either prime or they're the product of 2 non-principal primes, right? As an ideal. Everybody okay with that? Okay, now that I've got that observation under the belt, this makes this question. So let's suppose we have 2 irreducible factors. Let's say alpha 1, alpha 2. Now, one of the things that we learned sort of earlier in this class was that if you have a prime factor, right? If you have a prime factor, then it has to appear on both sides, right? Everybody agree with that? Remember, our ultimate goal is to show these two lengths are the same. If, for example, alpha 1 is prime, then that means it divides this side, so it has to divide one of the betas. So I can just pull it off. So if alpha 1 is prime, then without loss of generality, it's associated with beta 1, which is also prime, and we just pull that off, right? So let's just assume that none of these are prime, right? Because that's not adding. So that is, this is sort of like taking a reduced fraction. We were already assuming that we reduced it. So, right? Notice by our observation, each alpha I is Pi1, Pi2. Here, Pi1, Pi2 non-principal primes. And similarly, beta J is Q I1 Q I2. So you take this factorization and think of it in terms of ideals, and this is P11, P12, alpha 2 is P21, P22, and finally alpha n is P11, P12. Beta 1 is this. But prime ideal factorizations are unique. And I don't even care about the uniqueness here. I don't care about it, right? Because the length over here is 2 men. And the length over here is m. So I have unique factorization. Notice that, let me point out that if you have let's suppose so this is not part of the proof, this is just kind of a side note. We have P1 from PIs all distinct. No, that's prime. How many irreducible factors does alpha have in any given factorization? So suppose I have fixed irreducible factorization. How many irreducible factors does alpha have? It's got 2, right? By grouping any pair of those items together. So how many different factorizations does it have? Well, it's got a number. I'm going to write this sloppily like this. Right. This is generated by alpha beta, so let me say gamma delta. So alpha to a unit is gamma delta. And I can prove this other ways. think that's it, right? So in fact, you're not gonna have unique factorization, because notice, all these have length two, think of these principal ideals, but there's three different ones. By the way, what if all four of those were the same? So what if P1, P2, P3, and P4 were all the same non-principal property? Then actually in that case, because these are all the same. Yeah, it's all the same. And you might think, okay, what happens if three of them are the same and one of them's different, or if there's two pairs, whatever. And different ways, sort of different numbers, factorizations, but the links will all be two. Now, I think that what we've done so far is the less surprising direction. How about the more surprising direction, I think? So if you have an HFD, then it forces the class number less than 2. So I'm going to do for the other direction. Let's suppose so our strategy is this. We're going to suppose that R is not an HFD, and we're going to show your class. Let me point out that in the first part of the theorem, in the direction we've already shown, the class number plus center two plus HT, we didn't use anything fancy covering algebraic integers. Only definitely, right? We never used the prominent class, never used the constant use. We never used the class previous time. Here's the show. So I'm going to break this down into two cases. Suppose there exists an ideal class. Let's say I. Such that suppose that you have an ideal class in class group whose order is some number n that's actually bigger than 2. Suppose there exists such. And let me give you kind of can somebody give me an interpretation for that? Okay, so I do all this fancy stuff and say, well, okay, the order of this class is n bigger than 2. But what does that mean? What does that mean about the order of the ideal class? What's an interpretation with regard to the ideal I? Okay, that's right. So what this means is I to the n power is principal. And I to the n is not principal. N is a positive integer. It's small, right? So in other words, it's the smallest thing that I can jack I up to that power, and it gets it turns it into a principal. Right? Now, check this out. Since R is greater than, there's at least one prime ideal in every class. There exists prime ideal P in this class. So in other words, P varies by I from a principal ideal. Now, when I say principal ideal, I mean an element quotient. Right. So you might say, oh, Jim, how to multiply I by a principal ideal of P, or you can instead of bring them both. Okay, so P has the same property. P to the n is the principal ideal, and know what the small know what the small power is. So consider well, I know that this is principal, and let's say that it is generated by I know that any ideal in the ideal class of I, including P, if power of it is principal ideal. So there we go. What sweet and sexy thing can I say about pi? Pi is looking very lovely today because it is irreducible, right? Anybody justify that? Let's just suppose for giggles that pi is equal to A with A, B, dot. So let's suppose it's reduced. Well, this. Okay, so right. First observation is the ideal term of pi is close to principal ideal. But I know that pi is P to the n. And here's the cool thing about it also. I know that that prime ideal factorization is unique. Right? So that means that AB is P to the n. So, in particular, A must be P to the J, some J and B is P to the minus J. Now, my greater than or equal to 1, notice that if this were 0, that would mean A is the entire ring, which of course A would be a unit, right? I did say not units. N minus 1 is basically keeping that also from being, this from being unit, but and there's a contradiction because note since the order of the ideal D is n is because if P to the J actually is a principal ideal, some power J is less than or equal to minus 1, that's trouble. Because we said that the order was exactly right. So this is a terribly important observation. That is that since the order of P is n, that means, and because P is a prime ideal, that was very important also in factorization. That P to the n actually is generated by an irreducible element. Now, anybody know where we're going to go here? Okay, so now what we've done is if we have what this shows, we have an ideal class order n, then I can build an irreducible that is P to the n power, right? How does that go? Okay, there you go. Now, select Q and prime ideal in class of I inverse. By the way, we supposed to order. So what's the, and of course, let me point out that in the class by inverse, and no. Notice because the order of any element of the group is equal to the order of 10 votes, right? So the order of class I inverse is the same thing as, and of course, the class of I inverse is the inverse of class of I, right? Everybody okay with this? Okay. By the way, one thing does bother me a little bit here. That was, I didn't claim that all you need is just one prime in every class. What if I inverse is the same class as the class of I? Can that happen here? It actually can't. Well, under what assumption? How come? So what bothers me is I pulled the prime P out of the class of I, right? Now I'm pulling Q out of the class of I inverse. What if the class of I and the class of I inverse are the same? Now I have to pull two primes out of one class, but that's not an issue. Why? That is correct. The only way that the class of I and I inverse are the same class is if the order of class I is 2, right? And that's not accurate, right? There's an ideal class of order in there. But, so this is actually a different class. Well, so now what? Now we've got this irreducible here, and we've got irreducible here, and I see another way. So I've used the power of P to form an irreducible. I've used that same power of Q to form an irreducible. I see another way to form an irreducible. I spy another one. Where's Waldo? Well, what are you supposed to point was between picking P, Q, and inverse classes? What happens if I multiply? Press. Since these two are in inverse classes, and PQ alpha is again. And the argument is, again, suppose that alpha is xy. Now, that means that x and y are a subfactorization of factorization of alpha, right? The only subfactorizations are non-principal ideals, right? And so that can't happen. So alpha is also irreducible. Everybody okay with that? Now, what's this? Nothing up my sleeve, and this is probably very similar to what we did last time. Look at EQ. Let's go alpha n, which is n, which is whatever I. So the ideal alpha to the n is the ideal I gamma. And all the players here are irreducible. So there is this unit on. So C2 ideals are the same. This one is generated by alpha n, it's generated by pi gamma. That means those two generators must be by unit. such that alpha n is u to pi down. Now look at factorizations. They're in factorizations. Or in factors, I should say. It's two factors. And then so okay, so what about whittling this down to this? Oh, yeah, we're not that much. Yeah. What about whittling it down? So my initial assumption was assume that there exists an ideal class order in bigger than 2. The only thing that's left is assuming that every ideal class has order 2 except the principal class. And we'll assume that there's at least one ideal class order 2, because otherwise it's UFD. So now you're reduced to the following. Well, non-principal ideal class is order. Let me point out that for rings of algebraic integers, since the class group is finite, that means that we're down to the case of 2 element probability. But actually, it doesn't matter. That's not going to come up in the proof. Let me point out that so far in the proof, the other direction, the only thing that came up was the fact that every ideal class had a finite order. Right? So all I needed was that C, that ideal class order n bigger than 2, and then the end of the first class has to have the same order, and the product of those two principles. That's all I needed. I needed that ideal. There exists actually. The only thing I need there's primary class is there exists an ideal class finite order. So, if CLR bigger than 2, then okay, so we reduce this down to the case where every ideal class is 2. So if the class number is bigger than 2, what can we conclude? What is sort of the most economical thing? So what we've got, here's what we've got. We've got that this group where every non-identity element is order 2. And I know there's more than 2 elements in it, right? So every non-identity element is order 2, there's more than 2 elements in it. So what can I conclude? Yeah, I mean, this is almost silly, right? I can conclude that there's at least 4 elements in this group, right? Because if every element is order 2 and the group itself is not order 2, then it has to have a subgroup of order 4, right? So let me make this a little bit more precise. Then CLR contains a subgroup isomorphic C2, C2. I just take 2 distinct elements of order 2 and see what they generate, right? You'll have their sum, the identity, and then you'll have a little line filter. So I'm going to write the Klein filter additively. That's the principal class. This core class, principal. And the other three classes are symmetric, all order 2. That's kind of cool, because what that means is, the cool thing about this kind of two torsion class group is, if you have any two non-principal ideals, well, that's only true two, but notice that everything, if you have any non-trivial ideal, any non-principal ideal, when you square it, you get a principal ideal. Right? And if you have one here and here, if you multiply them together, you'll get an ideal here. It's in this class. So, right? So here's what I'm going to do. Select a prime for each non-trivial class. So we'll call this R there. That hopefully won't use the ring. Now notice that, and this is a very similar argument to what we've done before. Let's say Q squared and right, because in fact squarely, and what do you suppose is true about these three generators, alpha, beta, and gamma? They all have to be irreducible, right? Because alpha, for example, decomposes into two prime ideals. There's no way it can decompose non-trivial into principal ideals, because the only prime ideals that could contain those, which is this. Right? And there's one more. Okay, so I've made an irreducible out of P by squaring it, and irreducible out of P by squaring it. You see another way that I can make an irreducible out of these orange ideals up here. Right. What happens when I multiply P into P R? And pi is also irreducible, because if pi is A times B, then that means either PQ, PR, or QR has to be A. And no product of two of these are principal. Right? So that's kind of is the product of these three ideals, but no proper subproduct. So check it out. If you look at alpha, beta, gamma, side beta, this is the same thing as P squared, Q squared, squared R squared, which is the same thing as P, Q, R squared, which is so I get the identity of principal ideals. So there exists a unit in the ring. These two generators, the ideal needs to be associates. So this side has three irreducible factors, and this particular factorization is constructed, and this has two irreducible factors. So not. And that completes proof. Any questions on that? Okay, and let me actually get this. Thing. I want to look at how we can expand on this idea of playing around with the way the class group is, playing around with corners to get a different vision. But let me give you this theorem. I think I gave you a statement. I'm sure I gave you a statement. If it was correct, but the was strong. Yeah. Then each ideal is one half. And that is to say, given A and I can be split. Well, A and I minus. That's one. And then B must be more favorable. So the 1.5 generator property just means that basically you can select your first generator at random as long as it's not 0, and then you might have to be careful about the next step. Let me point out that when I say 1.5 generator, this also includes principal, because even if I has the principal ideal, you can pick anything you want here, and then if you're careful and select the principal generator, then you will find it. Okay, any questions on that? I think this is a good stopping point. We will talk a little bit more about the ideal classes, and we'll get into more general in the theory of rings. Any questions? Well, I hope you all have just a fabulous Thanksgiving break. Get some rest, well deserved, and we will see you all after it's all over.